Hello viewers and my dear students. Welcome to session 7 on thermal analysis. Here we'll have a demo on simple 1D heat conduction problem with convective heat transfer at one end, that is typically called as composite wall problem. See here, now in the previous sessions and all that, there was no convection. It was 1D heat conduction. In another problem, it was 2D heat conduction only. But here you have a convection. Convection, you remember, convection is defined as the process of heat transfer by the combined action of heat conduction and mixing motion. Convection heat transfer between the surface and an adjacent fluid is defined by Newton's law of cooling as Q is equal to HA Ts minus Tf, where Q is convective heat flow rate, A is area exposed to heat transfer, Ts and Tf are surface and fluid temperatures, H is convective heat transfer coefficient, which generally depends on density, viscosity, specific heat and thermal conductivity of the fluid and other things are. Okay, now if it is convection, if it is between the surface and the fluid, you can take it as HA Ts minus Tf. If it is between the fluid and the surface, you take it as HA Tf minus Ts. Okay, this convective heat flow rate depends on H. More the H, more will be the convective heat flow rate. Anyway, this is the thing. This is the basic thing you should know. Convection is defined as the process of heat transfer by the combined action of heat conduction and mixing motion. These things you are supposed to study in your theory class and all that. Now, whatever is required for this session, for this demo session, I am doing it. Okay. Now, see here, there is a typical problem here. There is a composite wall, comprises of three materials. It is typically called as a composite wall problem, like the previous one, what I told you, the basic problem, the furnace wall problem. In the same way, it is a composite wall problem. Here, there are three layers. The first layer 1, layer 2, layer 3. Layer 1 has a thickness of 0.3, layer 2 0.15, layer 3 also 0.15 meters, all in meters are given. Okay, and here the outer temperature is 20 degrees centigrade, and here you have the convective coefficients given. That is, fluid temperature is 870 degrees and convective heat transfer coefficient is 25 watt per meter square degrees centigrade is there. Okay, that means the fluid is here. The fluid is maintained at 870 degrees centigrade and the convection takes place from the fluid to the surface. Please understand, the convection takes place from fluid to the surface and you have that is film coefficient as 25 watt per meter square degree centigrade. Once this is the thing, they have asked find the rate of heat loss from the furnace wall and the wall interface temperatures using theoretical methods and using Ansys plane 55 elements. Okay, find the temperature plot, thermal flux plot, vector plot showing heat loss to the surroundings. These things have to be matched. Draw a graph of variation of temperature along the thickness of the composite wall and all that. These things can be managed. First, we'll know how exactly to do this problem theoretically. Okay, these are all the, I'm telling you, these are all the standard things, what exactly will be given in any of the exams and all that. And moreover, it is all required for you. You should know how exactly to do these basic problems in Ansys. Okay, this is the problem 2. Okay, this is as per the manual, it is problem 2. Okay, a composite wall problem. Okay, comprising of three layers, 0.3, 0.15, 0.15. First material is 20 watt per meter degree centigrade thermal conductivity. Second 30, this is 50. Okay, 20, 30, 50, and the heat transfer coefficient is, that is the convective heat transfer coefficient is 25 watt per meter square, and the fluid temperature is 800 degrees centigrade. Okay, now you see here, theoretical approach, convection. Q is equal to HA Tf minus Ts because it is from the fluid to the surface. See here, it is from the fluid to surface. In that way, you have to be careful here. Q is equal to convective heat flow rate. A is area exposed to heat transfer. Ts and Tf are surface and fluid temperatures. Okay, TF is the fluid temperature, that is 800 degrees and all that. I'll come to that. Now Q by A, this is the basic equation for when convection is involved. Q by A, thermal flux, okay, is equal to rate of heat loss from the composite wall per unit area, because Q by A I have taken per unit area considering convection. T infinity minus T naught. T infinity is fluid temperature. That is, as you see here, this is 800, this is 20, and you see here, this is surface, T surface, or T1 you can call it. This is T2, T3, or T4 or T0. Okay, T0 they are given T20. Okay, I am telling you again. This is the fluid temperature 800 degrees. The convection takes place from the fluid to the surface. By the time it comes here, it will be definitely lesser than 800 degrees. This has to be found out. This we call it as T1 or surface temperature, TS. This will be T2. This will be T3. This will be T4 or T0, whatever you call it. Okay, T0 since they are given, we'll stick to T0 only. Okay, please understand this is TS or T1. This is T2, T3, and T4 is T0, 20 degree. But right now we don't know this. We don't know this. We don't know this also. All the three things have to be determined. And also Q by A, also the convective heat flow rate also should be determined. Okay. Now you see here, Q by A, T infinity minus T0. This is all theoretical. 800 minus 20, 1 by HI, 1 by 25, plus first layer 0.3 by 20 is the thermal conductivity, the first layer. Next layer has a thickness of 0.15. Thermal conductivity is 30. This is 20, this is 30. Next layer has again thickness is 0.15 meter only, but thermal conductivity is 50. In that way, you substitute it. 800 minus 20, 1 by 25 plus 0.3 by 20 plus 0.15 by 30 plus 0.15 by 30. This equal to 12380 watt per meter square. This is the flow rate. Okay, this is rate of heat loss from the composite wall is 12380. This has to be verified. Okay, to find the surface temperature, TS or T1. Okay, I have told you no, just now, TS or T1. TS is this, TS or T1 is this, TS. This I'll tell you how to find out that. Okay, Q by A is equal to H into TF minus TS you take, because fluid temperature is more here. Q by A, since heat, see here, Q by A we have just now found out 12380. Okay, since heat flow, that is heat flow rate through each of the layers. Okay, since the heat flow rate through each of the layers will be same from here to here, and finally it escapes to the atmosphere. That means heat loss to the surrounding is also 12380, and heat flowing through different layers is also 12380. Okay, 12380 watt per meter square. In that way, what I have done here is to find surface temperature or T1, TS or T1, Q by A 12380, H is the film coefficient 25, TF fluid temperature 800 minus TS. Or TS you get it as 304.8. Okay, that is equal to T1 you can call it. Since heat flowing through each layer of the composite wall is same, 12380 watt per meter square. Okay, here next 12380 T1 minus T2 for the first layer I'll take. But T1 is the TS, surface temperature. L1 by Kn, first layer I've taken, first material I've taken, that has a thickness of 0.3, that is okay. 12380 is the same. T1 or TS is, was just now found out the surface temperature is 304.8 minus T2, L1 is 0.3 divided by K1, 20 you put, you should get T2 as 119.1 degrees centigrade. Okay. In the same way, to find interface temperature T3 also, do in the same way. Since that is heat flow rate will be same, 12380, it is between, that is it is for the second surface. Okay, T2 minus T3 you take. It is for the second one, T2 minus T3 divided by L2 by K2. Now you know very well, you just now found out T2. This is for the second surface. T2 you already found out. T3 you don't know. T2 minus T3, L2 by K2, 0.15 by 30 you take. T3 you get it as 57.2 degrees centigrade. Okay. Now see here. This, as you see here, you have just now got this as T1. This is actually you got it as 304.8 something. This is TS or T1. This is T2, you got it as some 119.1. This is 57.2. This is anyway 20. Even if you do in the same way, okay, find interface temperature, okay, this 1238 T3 minus T4. T4 is T0. Divided by L3 by K3 also if you have done, then T4, T3, that is T3 minus T4 if you have taken this, and since you have found out T2, now you see here, now 12380 T2 minus 3T, T3, L2, T2, T3 you have found out. Now T3 you already know. Now knowing T3, you could have found out T4. Okay, you could have found out T4. T4 is 20 degree. T4 is 20 degree means what you would have done is 12380 T3 minus T4 divided by 0.15 divided by 50 it is. I think it is 50. Okay, but in place of T3 you substitute 57.2. In place of T4 don't substitute. T4 you find out. T4 will be same as T0. That will be 20 degree only you get. Anyway, this procedure I told you, this is the theoretical methods or the theoretical method of finding interface temperatures, okay, and also Q by A, that is heat transfer rate through the composite wall. Now what we'll do is how to verify this using Ansys we'll do, okay. See here, we'll do this, how to verify using Ansys we'll do. In this way, you see here, as I told you, file, clear start new you do, okay, basically the same thing you do every time, okay, and file, change job name you do, change by default it will be the file, okay. Okay, you give some name, okay, Gurdat 1 or Gurdat convection, something you give, okay, new log and error files. That means exclusive log file I want for this, Gurdat 1 you give, okay. Now immediately you get this. And file, go for change title. In this title, this is 1D. Write down 1D heat conduction, convective boundary conditions and all that you do. Okay, now we'll continue this in the next session, that is session 8. Now we have come to the end of session 7. Thank you friends, thank you for watching, thank you.